Thank you very much, James. And now we welcome on stage Ashley Montanaro, co-founder of Phasecraft.
Great. Thanks very much, and thanks for coming to this talk. It's great to be here as part of the British invasion this afternoon. So I'm indeed Ashley Montanaro from Phasecraft, and I'd like to tell you just a little bit about some of the things we've been working on. Unlike the last few talks that you've heard, we're not a quantum hardware company, we're a quantum software company. But actually, we think of ourselves as the quantum algorithms company. And really, our goal is to develop the quantum algorithms that are going to enable practical near-term applications of quantum computing. And we think that developing these algorithms is a really important and also a very significant challenge. I mean, many of you may remember this amazing announcement of quantum supremacy by Google a few years ago, which was a fantastic scientific achievement. But the quantum circuits that they demonstrated then, and indeed the best most complex quantum circuits that have been demonstrated more recently, they're still a long way away from the complexities of some of the algorithms that we would like to run. So I've been shown here on the slide this nitrogen fixation algorithm from Microsoft, which wanted to have 10 to the 15 time steps, which is clearly a long way away from the number of gates that we can actually execute on today's quantum computers. And our goal is to bridge that gap, and not by developing better hardware, but by developing those better algorithms. Okay. And just to say a few words about the company, we were founded in 2018 by Toby Cubitt, myself, and John Morton. And the founders have more than 50 years combined experience in quantum computing. We all have previous academic roles. And we've built up to a team of around 18 people based in Bristol and London in the UK. This photo is from our sort of company retreat in the summer where we went to this nice country house. So that's what we're looking at, somewhat, I don't know, artistic there, I guess. So one of the applications that we think is the most exciting and plausible for near-term quantum machines is materials modeling. So using quantum simulation algorithms to model quantum physics and to solve hard modeling challenges, in particular to do with materials. And enabling these quantum algorithms and making them actually practical involves many stages, actually. Firstly, it involves using some kind of deep understanding of the physics of the system that you're looking at to simplify the modeling problem to something which you can actually solve, hopefully on a quantum computer. You then need to find a way of encoding it efficiently on that device, and then you need to actually design some efficient quantum algorithms to solve that encoded problem. And you need to put all these things together if you want to achieve significant speed-ups over what was previously known. And this is some work that we did. So we have a paper on the archive back in May. And in this work, we were looking at the complexity of simulating a number of sort of relevant materials for different aspects of material science, for example, batteries and solar cells. And we ended up finding significant speed-ups by developing these new algorithms. For example, around a million-fold speed-up over what was previously known in terms of time complexity for simulating strontium vanadate, which is an interesting material for battery and solar cells. And as part of this, we developed a toolchain that goes right the way through from inputting a description of a material all the way out to outputting a quantum circuit that simulates that material. So the complexities of these algorithms are still not quite within that of a sort of NISQ-era quantum computer that we have today, but it's a lot closer than it was prior to this. Okay. And just to get a sense of the sort of techniques that we use to get speed-ups like the ones on the previous slide, we're sort of thinking about efficient ways to improve quantum simulation algorithms, for example, simulating time dynamics of quantum systems. And Toby Cubitt, my co-founder, had this really nice idea involving working one level below the standard quantum circuit model in a model that we're calling the sub-circuit model, which uses this idea that if you have a quantum algorithm that has many small rotations in it, maybe it makes sense to not implement these rotations as sort of bang quantum gates one after the other, but actually to implement them as small rotations like within the hardware itself. So this would be what people call pulse level control sometimes. And it turns out that if you come up with some sort of nice decompositions of the gates that you want to do in your quantum algorithm, then this can lead to some very significant savings in terms of the expected complexity that you need for the algorithms. So, for example, for this famous Fermi-Hubbard model, which we just heard a bit about in the previous talk, we're able to show that if you use this sort of sub-circuit model, you can improve the complexity from about just over 1 million to about 260 quantum gates, sort of equivalent for time dynamics. So this is the kind of technique we're trying to use. And we're also implementing our algorithms on today's quantum hardware. So again, with this Fermi-Hubbard model, we were looking at producing the ground state of this, which is sort of a fundamental problem in condensed matter physics. We tried implementing this on Google's quantum hardware platform. And we had an algorithm which was 10 times as many gates as been used previously, 4 times as many qubits, and we were able to get some sort of physically meaningful results out, including the demonstration of this so-called Mott insulating behavior, which is a sort of fundamental physical property. So really our goal for the coming few years is to sort of bridge this gap between the sort of realistic materials that I showed on the previous slide and these sort of near-term hardware demonstrations that we've already put together today. So that's what we're trying to do. If you'd like to learn more, please feel free to talk to me or I guess any of the other speakers at the happy hour later on after the panel discussion. So thank you very much.